Okay, YouTube, in this video we're going to focus more on solving logarithmic equations, but we're going to solve the type that nobody likes, and that's going to be the type that's going to require us to use a little bit more algebraic manipulation here. And so what we're going to do is we're going to amend some steps here in order to solve a logarithmic equation. But let's see here, solving log equations. Basically, the first thing we want to do is this. If we cannot use the one-to-one property, one property, and there exists more than one logarithm, then what we will do is condense our logs using the properties of logarithms. So let me go ahead and make an amendment here. We will condense our logs into a single logarithm using the properties of logarithms. Then we'll exponentiate both sides with a base of b. So here's the deal, folks. The deal is there are going to be times when we're solving logarithmic equations, kind of like this example right here in number 4, where you're going to see that there's more than one logarithm. And so the idea here normally would be that we could just maybe take one of these logarithms and subtract it over to the other side, and what we would get is just two logarithmic expressions like log of 2x equals negative log of x minus 5. But see, here's the problem with this. In this case, we also have a plus 2 on the right side, and so because we have this plus 2, and because we have this negative we can't seem to get rid of, there's no way that we could just say that 2x is equal to x minus 5. So since that's the case, what we're going to have to do here is this. We're going to have to condense into a single log. So what this means is we're going to probably need to review our properties of logarithms pretty quickly here. So let's go ahead and review these. We would say that if we take the log base b of x times y, then we would get the log base b of x plus the log base b of y. And we refer to this as a product property. That is to say that, hey, if you take the log of a product, then you could write this as the log base b, okay, they both have to be both base b here, but of each factor in that product. So log base b of x plus log base b of y, and we add instead. So our product property says the log base b of x times y is log base b of x plus log base b of y. Then our quotient property, recall, is the log base b of any quotient here. Can really be written as the log base b of everything on top minus the log base b of everything in our denominator here. And then our last property was the log base b of a power, x to the n. It said you could take that power, you could put it out in front, log base b of x. So you could see that everything from left to right here, our product, our quotient, and our power rule, okay, those essentially expand our expressions. But because what we want to do is have a single log, what we're going to do is we're going to make an effort to condense our expressions. So what you're going to look for, essentially, is you're going to be looking for a sum of two logs, or a difference of two logs, or a log having a power out in front that we could put back. And essentially, these two especially, we're going to glue these back into their original expression. So because I notice that, and I'm going to write this over here again, we have log of 2x is equal to, plus the log of x minus 5 is equal to 2. Then what we're going to see here is that because we have the same bases on these are both the common log base 10, then we could rewrite this as the log base 10. I'm not going to write the 10 this time, but of 2x here, we're going to say 2x times, okay, our second argument here, which is x minus 5. And so all of a sudden, you can see that both of these logs have been put back together where this is like our x and this is like our y over here in this xy expression. So having this here, what this is going to allow us to do is this. We're going to, first of all, we're going to simplify in here. We're going to get log of 2x squared minus 10x equals 2. But because now that we have this log by itself, then what we could do is we could exponentiate both sides, having the same base as our log. So we say 10 to the power of log base 10 of 2x squared minus 10x, okay, is equal to 10 to the 2. So on our left side, we get this cancellation here. We get left with 2x squared minus 10x. And this is going to equal 10 to the second on the right side here. So now I'm going to put a big fat box around this. And one thing that I really want to make sure that I say here is this. This is a quadratic equation. So this is one big reason why I get a lot of kickback on asking people to solve problems of this sort, because they don't like to solve quadratic equations. But here's what I want to say. To solve a quadratic equation, number one is going to be this. Set equal to 0. Step 2 is going to be this. Factor and solve. So because it's been since probably the first semester since we've done a lot of these and other reviews, we would say that what we're going to see here is a situation where we're going to get this set equal to 0, and we're going to solve it by factoring because we have a second degree equation. So we're going to say that 2x squared minus 10x equals 100. If we were to take that 100 and subtract it over, we'd say 2x squared minus 10x minus 100 is actually equal to 0. So with something like this, when we factor, of course, you always check for the GCF first. I noticed that we could divide both sides of this equation by 2 here. So factoring out this 2, we get the 2 out in front here. We get x squared minus 5x. This is the 100 divided by 2 would be negative 50 here, 0. And so because we have this 2 out in front, in this particular case, because we have 0 on the right, we're going to go ahead and divide that 2 out. And what we get left with is this trinomial, okay, in quadratic form, where we can hopefully factor it and be able to solve this. So we'd say what two factors of a negative 50, okay, that we can think of add up to be a negative 5. And the two that come to my mind here happen to be, I suppose, a negative 10, but then a positive 5. So if this is the case, then either x minus 10 had to equal 0, or x plus 5 had to equal 0, because the product of these two things came out to be 0. So solving this, of course, we get x equals 10 and x equals negative 5. Now, here's what I want you to do. I want you to be wary of this here, because this negative 5 we're going to learn is what we call an extraneous solution. Now, extraneous solutions, I'll tell you, they come about when we algebraically work something out that seems to work out algebraically but wasn't necessarily the case in the first place. And so the reason why this happens, and I'll go ahead and point this out, is because we're solving for x, and in either instance up here, x is to the first power. That means we have one solution to this. But when we had put these together, like we did here, 2x times x minus 5, we ended up with a squared variable type, which introduced another algebraic solution, which might not have been a solution to this original equation. So what we would do necessarily is check out our solutions here and see if they work. So we get on the left side here, we have the log of 2 times, if we were to check out the 10 first, plus the log of 10 minus 5 equals 2. I just want to show you this here. I'm going to do some manipulation. We get the log of 20 plus the log of 10 minus 5 is 5 equals 2. And because I know that I can condense these here, I get the log of 20 times 5 equals 2. That is to say, the log of 100 equals 2. And I know this is a fact because, hey, you know what? 10 to the second power equals 100. Now, in terms of checking our negative 5 here, if we would have plugged that in, we would have gotten the log of 2 times a negative 5 plus the log of a negative 5 minus 5 equals 2. So simplifying this, we get the log of negative 10 plus the log of negative 10 equals 2. And this is certainly a lie, and the reason why I want to tell you this is because we can never take 10 to the power of something and get a negative output. And so we can't take the logarithms of negative values. That is to say, up here we say that because the domain of logarithmic function just generally does not include all real numbers, we have to check our solutions. So when you get a negative solution, I'm just going to turn you on to this right now. This should be just at least a red flag. If negative log solutions, okay, then check for sure. Because that's a red flag that you need to be looking out for an extra solution there. Cheers.